Hello dear students, in this video I'm going to explain RLC parallel connection with AC circuit. In RLC parallel connection with AC circuit, for example, if you are connecting a resistance, an inductance and capacitance in parallel connection, okay? What is this connection? This is parallel connection, okay? So in this circuit, the source is AC source. We have potential difference and current here, and in parallel connection, so you have to be very careful. The potential, the values of potential difference are equal. What do you mean by value of potential difference are equal? It means that the total potential difference across the source is equal to the potential difference across the resistance, equal to potential difference across inductance, and potential difference across the capacitance. But in series connection, we have learned the magnitude of potential difference are not equal. The magnitude of the current are equal in series connection. But in parallel connection, the magnitude of potential difference are equal. But the current, the value of the currents are different. It means that the magnitude of the current across the source is not equal to the current across the resistance, and current across the inductance, and current across the capacitance. So we can find the current for each of the substance. Like for example, we can find the current across the resistance, and we can find the current across the inductance and current across the capacitance. According to Ohm's law, V is equal to what? V is equal to V sub R. It means that potential difference across R is equal to VIR. Potential difference across inductance is equal to IXL. Potential difference across capacitance, IXC. Okay? So you can rearrange the equation. VR is equal to IR times R. VL, IL times XL. VC, IC times XL. So if you rearrange the equation, you can find the magnitude of the current across the resistance is equal to what? Is equal to V over R. So you are not required to write potential difference across R, potential difference across L, potential difference across C. Why? Because the values of potential difference are equal. There is no difference between them, okay? And the current across inductance is equal to V over XL. Current across capacitance is equal to V over XC. Okay? So by this way, you can find the value of the current at each instant or at each circuit. So what about the V total? VE total is equal to what? What is the total resistance? Is impedance. Okay, what is the total resistance? Is called impedance. Z is impedance. Okay, and if you rearrange the equation, you can find the current across the source. What is this? This is the effective current across the source, and also you can find the maximum current across the source. Okay, by Ohm's law is equal to what? Is equal to V over Z. V over Z. Okay, for example, if the question says find the total current or the effective current across the source, you have to use this equation. If the question says find or calculate current across each of the resistance, inductance, and capacitance, you have to use these three equations. Okay? To proving the equation of we have another equation to find for the total current. Okay. Now I'm going to prove the equation of the total current according to the phasor diagram. Okay. As you have learned it in a previous lessons, in a series connection or in a pure inductance, pure capacitance, and pure resistance. For the pure resistance, potential difference and current are in phase. This is IR. Okay? The potential difference across the resistance and the current across the resistance are in phase, in pure resistance. Okay? I and R in the same phase, it means that the phase difference is 0 between them. And in inductance, we said potential difference leads current. In inductance, potential difference leads current by phase 90 degree or pi over 2 rad. So is it possible to say current lags behind potential difference? Yeah, it's the same thing. There is no difference between these two statements, students. Be careful. If you say potential difference leads current, it means that current lags behind potential difference. The same statement, the same meaning, the same thing, okay? Current in inductance lags behind potential difference. By which phase? Pi over 2 rad. And in capacitance, we said potential difference lags behind current. Potential difference lags behind current. And also, you can say current leads potential difference. Current leads potential difference. By which phase? Pi over 2 also. Okay? Now, according to the Pythagorean theorem, can we calculate the total current or the current across the source? Yes. And the current across the source, I total or I effective total is equal to what? According to the Pythagorean theorem, we can make a right angle triangle here. Right angle triangle. Okay. So this is opposite. And this is adjacent. What we have in the adjacent? We have IR. We have what? I across the resistance. In the opposite, what we have? Because in the opposite side, we have two vectors that are in opposite direction. IC is opposite to IL. So that is why we have to write down here IC minus IL. Okay? So according to the Pythagorean theorem, IE total is equal to what? Is equal to adjacent square, IR square, plus, in the opposite, what we have in the opposite? IC minus IL. Okay? IC minus IL square. So, what is the angle between IC and IR? 90 degree. What is the angle between IL and IR? 90 degree. So, what about AC and IL? There is 180 degree or pi rad. Okay? To find the direction and the angle, to find the angle between what? The total current and potential difference or the current across the resistance, you can use this equation. Theta is equal to what? Tan inverse opposite over adjacent. What we have in the opposite? AC minus IL. IC minus IL over what? Over IR. Okay, so this is the proving of the total current across the source, i.e. total. Okay, now I'm going to prove the total impedance in the parallel connection of RLC, parallel connection RLC with AC source. How can you prove the equation of Z? As you know, according to Ohm's law, V total is equal to IZ. VR is equal to I sub R times R. VL, IL, XL, VC, IC times XC. Okay? So, what about if you rearrange the equation? I is equal to what? I is equal to V over Z. Okay? Instead of I total, write down what? VE total over what? Z. I total is not equal to VE total over Z? Yes. Okay? This is according to Ohm's law. Continue. IR is equal to what? IR is equal to VR over R. VR over R. Plus IC is equal to V sub C divided by XC minus VL over XL square. Okay. So according to this equation, in parallel connection, which values are equal? Potential difference or current? Potential difference. Okay, the values of potential difference in parallel connection are equal. It means that VE total is equal to VR, VC, VL. They all cancel to each other. Okay, they all cancel to each other. What is remain? 1 over Z is equal to 1 over R square plus 1 over XC minus 1 over XL square. Okay, so usually the question asks us to find the total impedance, not 1 over Z or the inverse of total impedance. So that is why we have to flip this side. We have to flip this side to find what? To find the total impedance Z, not 1 over Z. Okay, to find Z, if you flip this side, also you have to flip the other side. Okay, 1 over Z is equal to Z over 1, and the 1 is not written here, is equal to what? If you flip this side, this is radical over 1, it becomes 1 over this radical. 1 over this radical, 1 over R square plus 1 over XC minus 1 over XL square. Okay, so finally we proved the equation of Z in RLC parallel connection with AC source. Okay, so according to this equation, Z is equal to what? 1 over radical 1 over R square plus 1 over XC minus 1 over XL square. Okay, and also you can rearrange this equation because XC is equal to 1 over omega C and is equal to 1 over 2 pi FC, and XL is equal to omega L or 2 pi FL. You can replace into this equation. Okay, the equation becomes like we bring down this Z. Okay, 1 over R square. Instead of 1 over XC, write down what? 1 over omega C. It becomes what? 1 over omega C, and 1 over omega C, it becomes like the 1 over omega C. According to math basic, 1 over omega C is equal to omega C. Okay, minus 1 over omega L. So is it possible to write down here like that? Yes, of course. So which equation are correct to find the total impedance in parallel connection? Both are correct. Okay, and also instead of omega you can write down 1 over R square plus 2 pi FC minus 1 over 2 pi L square. Okay, so all are correct to find the total impedance in parallel connection. It depends on the question. For example, even the question XC and XL are given directly, you can find Z by using this equation. Okay, and also you can find the direction of the angle according the total impedance is equal to tan inverse 1 over XC minus 1 over XL divided by 1 over R. Okay, so you can draw the phasor diagram for the impedance like that. Okay, as you know, this is I across R, this is I across C, I across L. If Z is equal to V divided by R, the phasor diagram for the impedance, it becomes like that. And instead of IC is equal to what? VC over XC. It means that 1 over XC. Here what we have 1 over XL, and here we have 1 over R. Okay, you can draw the phasor diagram for the impedance. The total impedance Z is equal to what? Is equal to, here we have 2 vector opposite, 1 over XC minus 1 over XL, and here we have R. So that is why theta is equal to tan inverse opposite over adjacent. Okay, opposite over adjacent. Look, this is RLC parallel connection. In parallel connection, the circuit is connected with the inductance, resistance, and capacitance. Okay, according Ohm's law, you can write down this equation, and Z is equal to 1 over this equation, this radical. All of them are correct. Okay, look at this. Okay. As when the circuit is connected with the resistance and inductance, so you can skip the capacitance, or capacitance is 0, and also when in the case the circuit is connected with the resistance and capacitance, you have to remove the value of XL. Okay, so if the phase difference is positive, it means that XL bigger than XC. When does the theta is positive in parallel connection? When XL is bigger than XC. Okay, so for the theta is negative, XL is smaller than XL smaller than XC. So we have one question about the parallel connection. Okay, an AC source of effective value of 50 volt. What is this? This is the effective value of potential difference. AC source, the potential difference of the source. It means that this is VE total. VE total is equal to 50 volt connected across parallel. What is the connection? The connection is a series connection or parallel connection. Is a parallel connection. In parallel connection, the value of potential difference are equal. VE total is equal to 50 volt, and this 50 volt is for the resistance, inductance, and capacitance. Okay, the value of potential difference are equal. How did you know? Because the connection is parallel connection. Over resistance, the resistance is given R 300 ohm, inductor of impedance XL is given 600 ohm, and capacitor of impedance XC also is given 200 ohm. Okay, calculate the following. Impedance of the circuit, Z is unknown, so we have to solve one by one. Okay, the first branch is impedance is unknown of the circuit. How can you find the impedance of the circuit? Because the circuit was parallel connection, so that is why you have to use this equation. Okay, this equation, Z in parallel connection, Z is equal to what? 1 over R squared plus 1 over XC minus XL squared. Why do you have to use this equation? Because in the question, XL, XC, and R are given directly. That is why we have to use this equation. Okay, it depends on the question. Do we have resistance? Sorry, yes, was given 300. Okay, resistance replace here. Do we have XC? Yes, 200. Do we have XL? Yes, replace into this equation. By calculator, you can find in the total impedance is equal to 212 ohm. This is the total impedance in parallel connection. Okay. Now the second branch B. In branch B, what is unknown? Effective value of the current that passes through the resistance Effective value of what? What do you mean by effective value? It means that IE. IE across what? IE across the source, IE total. It means that, or IE across the resistance, IE across capacitance, or IE across inductance. It should be indicated. Effective value of the current that passes through the resistance. It means that IE, inductor, IEL, and capacitor, IEC. So, okay, it is very easy. First, you have to write down the equation of IR. According to Ohm's law, IR is not equal to V over R. Do we have the value of V? Yes, was given 15 volts. Because in parallel connection, the potential difference across the source and inductance, capacitance, and resistance are equal. V across the resistance also 50 volt divided by 300 is equal to what? Is equal to 0.166 ampere. This is the current across the resistance. Current across what? Resistance. The second one, current across inductance. According to Ohm's law, if IR is equal to V over R, what about IL? IL is equal to V over XL. V is constant because parallel. XL was given, it was 600. 50 divided by 600 is equal to 0.083 ampere. This is the current across the inductance. Current across the capacitance, IC, is equal to what? Is equal to V over XC. V 50, XC was given 200. 250 divided by 200 is 0.25 ampere. Okay? So which one has the greatest current? The current across the capacitance has the biggest value. Okay? Now, this is branch B, okay? Branch B. Branch C, what is unknown in branch C? The value of the effective current of the circuit. Effective current of the circuit, it means that IE total. IE total. So you can find by using two equations. How can you find E total in parallel connection? In two ways. The first way, IE total is equal to V over Z. IE total is equal to IR square plus IC minus IL square. It's up to you. If you have the potential difference and Z, you can use this equation. This one is the easiest way. But in the case, if you don't have Z, you can use this equation to find the total effective current across the source. Okay, so here we use the Z to find, because we found Z. IE total is equal to what? VE total, the same 50 volt divided by Z. Do we have Z? We didn't have, but we found it. 212 is equal to 0.235 ampere. This is the total current across the source. Okay, this is branch C. The last branch in this question, in the question 56, there is a difference angle between the total current and the potential difference. Yes, absolutely. How can we find this angle? Between what? The total current and potential difference. This is IE total and this is potential difference. To find this angle, how can we find this angle? By using this equation. Theta is equal to what? Tan inverse. Opposite over adjacent. What we have in the opposite? IC minus IL. Here we have IL. IC minus IL over IR. Do we have IC? No, we didn't have, but we found it. IC was 0.25. IL, yes, 0.083. IR, 0.166 ampere. Replace into this equation. The theta is 45 degree. Okay, so the currently this is the potential difference because the theta is positive. Okay, so that is all about the RLC parallel connection. Hope you enjoy and get benefits from my lesson. Thank you very much. Inshallah, I will see you in the next video. Thanks.